Hi everyone, my name is Jyotika and I'll be talking about pyAudioProcessing, which is a Python-based library for building audio classification models. Before I dive right in, I want to quickly introduce myself. My name is Jyotika Singh and I work as the VP of Data Science at i6 Media, which is a content and audience intelligence company based in Washington, DC. I've attached my social media accounts here. Specifically, I'll be posting this slide deck after the conference on my Twitter handle. Also, in case anybody has any questions that you're not able to ask during the conference, you can reach out to me on Twitter. So diving right in, pyAudioProcessing is a library for everything audio analysis, visualization, classification, all of that. From anything starting from changing between audio formats for your data, to cleaning, removing silences or low activity areas from your data, to extracting features that are relevant for audio, to training machine learning models, using your own custom backend or popular scikit-learn classifiers, and also actually leveraging some pre-trained models to help establish a baseline. So all of that is something that you can do with this library. Now, for someone new to audio, the whole audio processing domain, what features, what is this MFCC, GFCC, spectral, all of this, may not be clear. So we'll quickly dive into a few things before we get back to the library and how to use it. So that'll be an overview of machine learning, what an audio signal is, audio features, where the inspiration comes from, and then pyAudioProcessing, the kind of things you can do with this library, followed by some actual audio classification examples that were accomplished using pyAudioProcessing library. So diving right in, machine learning at a high level consists of three main stages. There's a data stage, which consists of data collection, any sort of data cleaning, whether that's manual or using some process. And then you transforming of your data into numerical features. Features is a very common term for machine learning language. So it's basically numerical representation of your data. And this is what goes inside a machine learning model to train your model. And then when you evaluate the model, that further influences your data decisions, like what you want to do to clean your data, if that's an issue for your model, or what kind of features do you extract from it. So this entire process is more of a high-level baseline of what machine learning is. And if you consider something like images, behind what we see in an image are these pixel values, and what kind of transformations make sense for images is, let's say, if you want to detect shapes or a sudden transformation in colors. So those kind of filters apply to these RGB values for an image, then help you do things like edge detection. For text, something like a word vector representation is something that makes sense to numerically represent text. So we see there are different types of methods to numerically transform data, and it depends on the data at hand. So it's different for image, it's different for text, and we can't use what we use for text for something like an image or even audio. So we'll be looking into what these are for audio and what really audio is. So an audio signal is a signal that vibrates in the audible frequency range. So now that I'm talking and you can hear me through the speakers, what that does is it creates air pressure signals. And then when our ear receives it, it transforms into signals that the brain can understand, and then the brain interprets this audio as something meaningful. So that's really what audio is. And they're really great Matlab tools for audio processing in particular, and digital signal processing in particular. So there's a lot of research that goes on where people are experimenting with different features, transformation, just audio processing in general, and they quickly make their way to Matlab. And comparatively, Python has been a little bit behind, but now there's so many great research and development happening in Python as well. And we'll be discussing some of the tools involved there. So there are two terms that are particularly important when thinking about audio signals, spectrum and cepstrum. So let's quickly just learn about what these are. So spectrum is your representation of your audio signal in the frequency domain. What does that mean? Whenever a sound is spoken, or basically consider an audio signal where somebody's just saying a vowel like Now what happens is when you're saying this, you may not feel it, but This signal has a frequency, and how a signal can be represented in terms of a series of sines and cosines helps us determine these frequencies, and that is essentially also called Fourier transform. It's transforming a signal from time domain to frequency domain. So that is spectrum, is essentially signal in frequency domain and gives us important information about the sound. Now, if one takes log magnitude of the spectrum and then inverse Fourier transform, what happens is we have a signal which is called cepstrum. Now, cepstrum is neither in time domain nor in frequency domain. Why not in time domain? Because we took an inverse Fourier transform before getting to the cepstrum, but after taking a log magnitude of the spectrum. And why not in frequency domain? Because we did take an inverse Fourier transform. So cepstrum is a domain of its own, and it does convey a lot of useful information about the signal. So visually, these are how the charts look like for a particular vowel, how the spectrum looks, how the cepstrum looks. And in machine learning, typically the first 13, sometimes the first 20 cepstral coefficients are considered to contain a lot of important information about the audio, and they form as great features for building machine learning models. So why frequency domain? Why do we care about all of that? So all the inspiration really comes from biology and how our ear works. So our ear is composed of so many different components, but one in particular that I want to mention is the cochlea, which is a spiral fluid-filled structure, and it has thousands of tiny hairs. These hairs are of different length, and the shorter hair are known to resonate with the higher frequency sounds, and the longer hair are resonating with the lower frequency sounds. So it's almost like the ear, when the audio signal passes through the ear to the brain, it's like it's naturally a Fourier transforming the signal. So it's treated as like a ear is a natural Fourier transform analyzer, and a lot of the features that we use to train machine learning models for audio actually take inspiration from how our ear works. Audio features. Now there are so many different types of features here, but we'll be talking about a few of them, the more popular ones, and I'll be listing the rest of them in a separate slide just in case anybody wants to dig in further. So one very good feature, very popular, used in extensive amount of applications for audio classification, is the Mel frequency cepstral coefficients. Essentially, if you see how the filter looks like, they're just a bunch of triangles, and they get wider and wider as the x-axis increases. The x-axis is nothing but frequency, and it's known that our ear gets less frequency selective beyond 1 kilohertz. So that's why we are trying to broaden the filters as we go ahead in frequency. So this is inspired again from how the human ear works and how really the biology of all of it works. But essentially the mathematical way to get to it is the spectrum is passed through this Mel scale filter bank. The log magnitude is taken of the resultant and followed by a discrete cosine transform. The discrete cosine transform's job is to just capture the high level shape of the signal and ignore like the minor changes, because that's considered to be mostly noise. Discrete cosine transform also finds applications in JPEG compression and so on. So what results is the MFCC feature, and it is used in a variety of audio classification applications. Another very popular feature is called the gamma tone frequency cepstral coefficients. So very similar, except now you see the filter looks a little bit different in that its shape, it's more smooth around the edges on the top. So this again takes full inspiration from how the human ear works, and this gamma tone filter bank is also considered as the front end simulation of the cochlea. So this is supposed to more closely represent how the human ear works. Spectrum passed through the gamma tone filter bank, followed by some downsampling, loudness compression, and discrete cosine transform gives us the GFCC features. If you were to look at it visually, that's how an MFCC feature looks like, and that's how GFCC feature looks like of a same audio signal. There's so many other features that have gained prominence in time in over the last many years, and so I just want to list them out here. We won't be talking about all of them, but certainly if anybody is interested in further exploring more audio features, I've also attached some names here and some links in the resources slide, which will be towards the end, so hopefully that helps. So before we jump into pyAudioProcessing as a library, we discussed audio features and really what audio is. So does that really mean we need to do all those mathematical calculations before we can get any audio features? Well, the good news is no, because now that we know how to do this calculation, there are tools out there, libraries that actually contain the implementation. So all you need to do is just use the library and use the implementation that's already there. So with that, this is a slide we saw very much in the beginning. Now this makes sense. We know what is MFCC, GFCC, we know what's a spectrum. And there are so many other audio features that the library helps you extract. You can extract these features, use them with your own classification model, or there's a built-in functionality to use a scikit-learn model, and then it'll do hyperparameter tuning on your behalf. So let's take a deeper look. This library has actually found usage in so many applications and has been cited in works across in the last few years, especially whether it's anything to do with acoustic signals or speech emotion recognition. Essentially anything that involves dealing with audio, classifying audio, extracting any features from audio, you will find this library useful. So this is the diagram we saw very much earlier when we were talking about machine learning at a high level, the 3 phases and everything. So now this is the same diagram, but very specific to audio and pyAudioProcessing library. Data collection is a separate topic, but there are so many resources where you can have publicly available data. You can access that and really work with the audio that you get from these publicly available data sets. The link is attached in the resources slide. If you have your own data set, you can use that as well. But once you have the audio, there's some sort of cleaning. Sometimes, your audio is a little bit noisy, or your component is, let's say, speech, and you have a lot of silence, before and after or in the middle, and you want to just get rid of that. You're mainly interested in the speech. So there are some data cleaning techniques that you can pass data through before training your machine learning model so that your data is in a more cleaner state. So these data cleaning and pre-processing techniques are implemented. Some of them are implemented in pyAudioProcessing, where you can, to clean your audio, you can remove any low activity segments so that you're only passing in your more relevant pieces of information of your audio. And then you can also convert between audio formats. You'll find in a lot of places, WAV is the format that is accepted, or there's a lot that you can do with WAV compared to other formats, though that's slowly not going to be true because everything is developed in a much flexible manner going forward. But if you ever need to convert your audio between different formats, you can do that as well as a data cleaning or pre-processing step. Numerical features, you can extract features. You can either use them directly with a scikit-learn model, or you can just extract them and use them as a completely separate classification backend. So there's that method for it as well. Coming all the way to training, you can train scikit-learn models directly, or you can even build your own. And then evaluation, the library automatically calculates confusion matrices and gives you a cross-validation summary of your training. So you can use that for your evaluation metrics as well. So at a very high level, how can you use this library? Let's say you have audio. Ask yourself these questions. Does it need to be converted to WAV? If yes, use pyAudioProcessing convert audio module. If not, does it need to be clean? Use the specific pyAudioProcessing module to clean it. If not, you want to create a scikit-learn classifier, there's a method for that as well. If you want to use, just extract the features to use with your own custom classification model, you can do that as well. If you don't want to do that either, you just want to use take your audio and pass it through a pre-trained model. There are 3 available in the library as well as a part of the library that you can use to just establish baselines. So you can just pass in your data through the classifier without really doing anything else. And if not even that, do you just want to visualize your audio? Do you just want to see how your signals look? You can do that as well. If none of them suit your need, if there's anything else, please help out the contributors of this library and create an issue or a discussion item on GitHub so that we can help you get to whatever you need that is not already there. So a little more about the functionality. It's compatible with Python 3.6 plus. It's been specifically tested for 3.6, 3.7, 3.8, and 3.9. There are many ways you can get started using pip install, or you can do git clone and then the setup steps. All of this is in the README of the library. There's so many audio features that you can extract: GFCC, MFCC, spectral features, different chroma features, and then there's LPCC as well, which is currently under implementation and will be available soon. Furthermore, the classifiers, the scikit-learn classifiers that you can use directly to train your audio are things like SVM, random forest, logistic regression. Again, any most popularly used scikit-learn classifier options would be easily available for you to use. Furthermore, cleaning, removing of silence and low activity segments is what is already implemented, and there's other techniques which take your frequencies that are going on around your signal and just subtract it, the low segments ones with the entire signal, in order to clean the audio, even in the components where there isn't a speech or an actual signal of use present. So essentially, when people are producing audios in a noisy environment where there's background noise, techniques to clean that up as well. And it's coming soon. It's again under implementation, but all these functionalities would be available. Converting audio formats, as we have discussed, visualizations in time series, in frequency domain, the spectrograms, which is a combination of time series and frequency domain, and then also pre-trained models like I was specifying. So there are 3 available in this library. There is a classifier that classifies between speech and music. Another classifier to do music genre classification between 10 music genres, and another one to do speech versus music versus bird sounds classification. So it'll be able to decipher your audio between 3 different classes. So now that we have learned about the library audio features, let's actually talk about some audio classification examples that were built using these things that we've just spoken about and the pyAudioProcessing library. So the first example we'll look at would be audio type classification. And in this, we'll be classifying the signal into 3 potential classes. It'll be speech, music, and birds. The training data set were 50 samples per class, so total 150 samples. The classifier backend was fixed to SVM as for this experiment purposes. And then testing data was 14 samples per class. So 3 different experiments were run with this classification problem, where we are trying out different features to solve for the same problem. So in the first one, we just use MFCC as the audio features, train the classifier, and the confusion matrix you see on the screen at the absolute left is a result of that. And it looks pretty promising. And even the test results look very, very promising. The classifications look pretty good, and the classifier seems to be doing really well. Just for experimentation purposes, switching to GFCC feature alone without MFCC, we see that classifier does pretty well too. And there are areas where it may be doing a little bit better than the MFCC one, and the other way around as well. Regardless, both individually seem to be proving out to be good classifiers. And then we can also combine these different features. You can specify multiple features to use in conjunction with each other. So MFCC and GFCC together. And that classifier also seems to be giving good results. As we can see on the absolute right, that's the test results for each of these different features that were tried out. So this shows the capability of the features itself. Like when we extracted MFCC from audio, it definitely contained something that's helping the classifier decipher between these classes. And so is GFCC separately, and so is combining GFCC and MFCC features. So such sort of features capability is what we're trying to showcase here. And in this case, if we were to try different classifiers, we could see totally different results as well. But just for the functionality of seeing how the features impact the model, this experimentation was performed, and we can see this is how the MFCC feature looks like for the 3 different classes for a sample signal. And we see, okay, the features definitely are conveying some sort of a different pattern for these samples. And if we compare GFCC and MFCC for speech, music, and birds, we see even the features itself are conveying completely different information. So it's not like anything in GFCC is redundant from what we already have with MFCC in this example. So they're both different features and conveying different meaning in this case. Let's consider another example for music genre classifier. And in this case, we have 10 music genre classes. It's the GZ-TAN dataset. It's a very popular dataset. Link will be in the resources slide. And we used 80 samples per class for training and 20 samples per class for testing. So first, we are just going to use MFCC to see how this works out, and we'll keep classifier again constant at SVM for experimentation purposes. And we see on the left the training confusion matrix. It looks like for some classes it's doing all right. For some classes it's not doing that great. And we can see that trend from the training confusion matrix itself. And when we look at the testing data performance, we see that, well, okay, classical is doing good, but blues is completely off. Hip hop, we have really less correctly classifications in the test data set. So this is how the MFCC is doing. While this may not be a great classification for everybody's classification model for everybody's use case, it still shows capability because it's able to decipher between the different music classes to some extent. So let's see if we can improve it using different features. So as another set of experiment, we added GFCC, spectral and chroma features to the same model to see whether adding more features, and specifically these features, has made a difference. So certainly the confusion matrix on the training data looks a lot better for every single class. And on the right, we have a comparative study between the previous slide that we saw and how these features have improved the current results on the test data. So now we see disco, we only had 4 out of 20 correctly classified, and now we have 13. So there is a very big improvement, and we see mostly there is improvement except for jazz, but overall every single class is now doing better. And this is just with experimenting with more features and adding more features that is available with the library. Further, a lot of assessments can be done by looking at how the test data was performing, where the incorrect classifications were happening. So in this example, we see that reggae in particular, is really confused with hip hop a lot in the classifications. So really, next steps could be digging into the data set itself, how clean the data is, whether there's anything that could help on that data phase itself and the cleanliness of data phase. Other things could be, experimenting with further features and of course different classifiers because we only used SVM here just to establish an exercise and a baseline, but experimenting with further other backends. Specifically nowadays there's a lot of deep learning backends that have been particularly useful in classifying these audio music genre classification tasks. So using all of those can be beneficial as well. So there's a lot of things that one can experiment with just for showing of the capability. We can do all of these experiments using pyAudioProcessing library. Here's a much promised resource slide. It contains links to a lot of things that we could not talk about in depth and some other Python tools as well. One thing I do want to mention about main inspiration why I created pyAudioProcessing was a few years ago I was working on this audio classification project and I wanted to use Python for it. Machine learning has been really popular and with Python, and Python has been the language of choice for majority of machine learning tasks. So I wanted to do that in Python, where I wanted to use GFCC features with some Python scikit-learn based classifiers. And I was not able to do that with existing tools. I had a lot of Matlab code for it, but nothing in Python. So I really worked to create the features using Python code and created the GFCC features and a lot of other audio cleaning features that I found were missing, and the gap, that was the gap that I noticed in the audio processing community in Python. So I continue to do that with every time I notice these little gaps, and it's an open source project. Feel free to work on some of the very beginner friendly issues. And please create the issues or the tickets in GitHub if you notice any further gaps in the community. Finally, I want to say thank you very much to all the organizers, all the attendees, everybody for tuning in. It's been a pleasure talking about this tool with all of you. I really hope to see you all again next year.